Comets don't copy each other. They follow predictable paths, obey gravitational laws, behave like frozen relics from the solar system's birth. So when Comet R2 SWAN spontaneously developed the same sunward-facing tail and plasma jets as the interstellar anomaly, 3i Atlas, astronomers had no framework to explain it, but the mimicry is just the surface. Right now, these two objects have positioned themselves on opposite sides of Earth, a perfect pincer formation along the ecliptic plane. Orbital mechanics can create patterns, sure, but coordinated arrivals, that requires intention, or at least intelligence we haven't accounted for. By the end of this investigation, you'll understand why some researchers have stopped calling this astronomy and started calling it surveillance. If you're as captivated by these mysteries as I am, drop a like and subscribe. You won't want to miss what happens next as this story develops in real time. Leave a comment telling us where you're watching from, what time you've got on the clock, and whether you think we're being told everything about these paradigm-shifting discoveries. Part 1. Opening hook. We are being flanked. Two objects, that's what we're tracking right now. Two comets hanging in our sky like silent sentinels, positioned on opposite sides of the Earth along the ecliptic plane. One arrived from interstellar space, the other supposedly crawled out from our own solar system's frozen archives. And here's the thing that should make your skin crawl just a little. They look almost identical. Same bizarre tail structure, same plasma jets, same defiance of what comets are supposed to do, on opposite sides of our planet, right now. This isn't some vague astronomical curiosity buried in a journal nobody reads. This is happening above your head tonight, while you scroll through your phone or argue about dinner plans. Two objects that have no business resembling each other are performing the same cosmic dance, bracketing our world in what military strategists would recognise immediately as a classic pincer formation. We are, for lack of a more diplomatic term, being flanked. Let me introduce you to our players. First, there's 3i Atlas, discovered on July 1st, 2025, by the Atlas Survey System in Hawaii. The moment astronomers calculated its trajectory, alarm bells started ringing in observatories worldwide. This thing wasn't just passing through our neighbourhood. It came from outside, from the space between stars, screaming toward our sun on a hyperbolic orbit with enough velocity to prove it had never been bound to our solar system. Ever. An interstellar interloper, only the third confirmed visitor of its kind, scheduled to whip around the sun at perihelion on October 30th, 2025, before vanishing back into the cosmic void. Then there's C/2025 R2, designated SWAN after the SOHO spacecraft's instrument that caught it on September 11th, 2025. At first glance, SWAN seemed unremarkable. Just another long-period comet, probably kicked out of the Oort cloud millennia ago, now making one of its rare passages through the inner solar system. Astronomers catalogued it. Amateur astrophotographers added it to their imaging queues, and everyone assumed it would behave like comets are supposed to behave. Predictable. Boring. Safe. Except SWAN didn't get the memo. Within weeks of discovery, its brightness exploded, soaring through magnitude levels faster than models predicted. Telescopes around the world swiveled to watch, and what they saw made people start asking very uncomfortable questions, because SWAN was developing features it had no reason to possess, features that looked disturbingly familiar to anyone tracking 3i Atlas. Both comets now display extended tails and coma structures that shouldn't exist given their different origins and orbital mechanics. Both show what observers are describing as plasma jets, or ionized gas emissions oriented in ways that violate the usual comet playbook, and both are doing this, simultaneously, on opposite sides of Earth's orbit, like cosmic bookends framing our tiny blue marble in three-dimensional space. Let me show you what I mean. Pull up any recent image of 3i Atlas from NASA's archive, or from the growing army of amateur astronomers documenting this thing. You'll see a fuzzy coma, that cloud of gas and dust surrounding the nucleus, stretching into an elongated tail. But look closer at the geometry. That tail isn't pointing away from the sun like every elementary school science poster teaches you. Parts of it seem to face toward the sun, or at angles that suggest something more complex than simple solar radiation pressure pushing dust away. There are jets, streaks of brighter material shooting out from the nucleus in directions that change as the comet rotates. Now look at SWAN. Different comet, different orbit, different origin story. But the morphology, the shape and structure of what you're seeing, bears an unsettling resemblance. extended coma, tail structures that don't quite follow the rules, jet-like features that have observers arguing about what they're actually looking at. It's like watching two completely unrelated people develop the same rare birthmark in the same location. Possible? Sure. Probable? That's where things get uncomfortable. The question looming over this entire situation isn't just about comet tails or plasma physics. It's about position and timing. 3i Atlas approaches from one direction, SWAN from another, and Earth happens to be caught between them along the ecliptic plane, that flat disk where most solar system action occurs. Viewed from above, we're sitting in the middle of a cosmic pincer, with two objects exhibiting matching anomalous behaviour, closing in from opposite sides. Is this a coincidence? Are we witnessing some bizarre convergence of independent physical processes that just happen to produce similar results at the same time? Or is something else happening here? Something that requires us to consider possibilities that sound like they belong in science fiction rather than peer-reviewed astronomy? Before you write this off as sensationalism or panic-mongering, understand that these aren't idle speculations from internet forums. These are documented observations from professional astronomers, confirmed by multiple independent instruments, photographed by people with decades of experience who know the difference between a real feature and an image artifact. The data is real. The resemblance is real. The positioning is real. What we don't know yet is what it means. That's what keeps serious scientists up at night, staring at their computer screens, running simulations, checking their math over and over, hoping to find some ordinary explanation that makes this whole thing make sense. Because the alternative, the possibility that this resemblance is not coincidental, opens doors that most of us would prefer to keep closed. So here's where we start. Two objects, same. Strange appearance, opposite sides of Earth, and in the sections ahead we're going to dig into the data, test the hypotheses, and see if we can figure out whether we're watching a cosmic coincidence or something that demands a completely different kind of attention. Because right now, whether you're aware of it or not, we are being flanked. The only question is whether anyone or anything is actually aiming. Part 2, Raw Orbital Geometry, Ephemerides, and the Sky Multilateration Puzzle. Let's talk numbers before we let our imaginations run wild. Because the first thing any skeptic should demand, and rightfully so, is proof that these objects are actually doing something weird. Not just speculation, not just dramatic photographs with aggressive contrast stretching, but cold, hard orbital mechanics. The kind of data that doesn't care about your feelings or your narrative preferences. Orbital elements don't lie. They're the most fundamental description of how an object moves through space, defined by parameters like eccentricity, semi-major axis, inclination, and a handful of other numbers that tell you exactly where something has been and where it's going. When you plug these numbers into software, you can rewind time or fast-forward it, watching objects trace their paths through the solar system with mathematical precision. 3i Atlas has orbital elements that immediately mark it as an outsider. Its eccentricity, the measure of how elliptical or circular an orbit is, exceeds 1. That means hyperbolic, not bound to the Sun, not now, not ever. This object approached from interstellar space with a velocity so high that the Sun's gravity could only bend its path, not capture it. It'll swing around perihelion, that closest approach to the Sun scheduled for October 30th, 2025, at a distance still safer than Mercury's orbit, and then it'll accelerate back out into the galaxy. One-time visitor, no return ticket. The trajectory tells us where it came from, more or less. Astronomers have calculated that 3i Atlas entered our solar system from a direction in the sky that doesn't align with any known stellar system particularly close by. It's been travelling for thousands, maybe millions of years, through the frozen vacuum between stars, and only now has gravity pulled it through our neighbourhood. Its velocity relative to the Sun clocks in at dozens of kilometres per second, faster than anything born in our system could achieve without a massive gravitational assist. Now shift your attention to SWAN. This comet's orbital elements tell a completely different story. Its eccentricity sits around 0.994, just shy of 1. That means it's bound to the Sun, but barely. It's on an extremely elongated ellipse, the kind of orbit that takes it from the inner solar system, where we're seeing it now, out to thousands of astronomical units, deep into the realm where the Sun's influence fades and the Oort cloud lurks. One complete orbit takes centuries, possibly millennia. SWAN has been here before, probably many times, swinging past the Sun on a slow cosmic pendulum, then retreating into the outer darkness for generation after generation of human civilization. Its perihelion, closest approach to the Sun, brings it to about 0.5 astronomical units, roughly half the distance between Earth and the Sun. That's close enough to heat up significantly, vaporizing ices, releasing gas and dust, creating the coma and tail we're observing. SWAN is a native object, born in our solar system's primordial disk, kicked into its current orbit by gravitational interactions with giant planets billions of years ago. So here's the problem. These two objects, 3I Atlas and SWAN, have origins separated by unimaginable distances and timescales. One is an alien, the other a local. Their orbital planes intersect Earth's position along the ecliptic, but they approach from vastly different directions. If you visualize the solar system from above, 3I Atlas comes in on a steeply angled trajectory, while SWAN follows a more traditional comet path aligned with the ecliptic plane. They're not converging from the same region of space. They don't share a common ancestor or launch point. Plug their orbital elements into simulation software and watch them move through time. Rewind the clock. 3I Atlas came from interstellar space years ago, building speed as it fell toward the Sun. SWAN has been looping through the outer solar system for its entire existence, only recently diving back toward the inner system on its latest pass. There's no moment in the past where their trajectories overlap, no shared parent body that split apart, no fragmentation event that could have sent them on divergent paths. This is what makes the morphological similarity so confusing. If these comets came from the same source, their orbits should reflect that. We'd see evidence of a common origin point, similar velocities, perhaps other fragments scattered along related trajectories. But we don't. The orbital geometry screams that these are independent objects with zero connection to each other. One is passing through, the other is coming home. They shouldn't look alike, yet they do, and that's the puzzle astronomers are wrestling with right now. Because if the orbits rule out a shared origin, then any resemblance in appearance must be caused by something else. Some physical process acting on both comets independently that just happens to produce similar results. Or, and this is where things get uncomfortable, some external influence that doesn't care about their different origins and is affecting them simultaneously despite their separation. Astronomers have run the numbers backward and forward, checking for gravitational perturbations, hunting for minor planets or undiscovered bodies that might have influenced these orbits in ways that could create apparent connections. Nothing. The dynamics are clean. 3I Atlas is hyperbolic, SWAN is bound, end of story. If there's a link between them, it's not written in their trajectories. This creates what I'm calling the sky multilateration puzzle. In navigation, multilateration uses signals from multiple known positions to triangulate an unknown location. Here, we have two objects at known positions, exhibiting similar signals, the morphological features, and we're trying to figure out if there's an unknown source causing both. But the orbital math says there isn't. They're too different, too disconnected, so either the resemblance is pure coincidence, wildly improbable but possible, or we're missing something fundamental about how these objects are behaving or being influenced. The next few sections will dive into what those morphological features actually are, whether they're as similar as they appear, and what physical processes might explain them. But for now, understand this. The hard data, the orbital mechanics that can't be faked or misinterpreted, tells us these comets should have nothing in common. That's what makes their apparent mimicry so difficult to explain away. The universe just handed us two objects that defy the most basic expectation, that origin determines behaviour, and now we have to figure out why. Part 3. Morphology. What the images really show. Let's talk about what you actually see when you look at a comet, versus what's really happening. Because the human brain is a pattern recognition machine that evolved to spot predators in the grass, not to accurately interpret the three-dimensional dynamics of sublimating ices in microgravity. We're really good at seeing faces in clouds and conspiracies and coincidences, which means when it comes to comet morphology, we need to be brutally honest about the difference between observation and interpretation. Comet imaging is deceptively complex. You're not taking a selfie of a rock. You're capturing photons that have bounced off or been emitted by particles of dust and gas, scattered across hundreds of thousands of kilometers of space, viewed from one specific angle at one specific moment in time. Change your viewing angle, change the time of observation, change the filters on your camera, and the comet can look completely different. It's like photographing a firework from different sides of the park. Same explosion, radically different pictures. When people say 3i Atlas has a sunward-facing tail, they're describing something genuinely odd. Comet tails, according to every textbook, should point away from the sun. That's because solar radiation pressure and the solar wind push gas and dust outward, creating those iconic streaming tails that always orient opposite to the sun's direction. It's one of the most reliable rules in the Comet Handbook, so when observers report a tail component pointing toward the sun, eyebrows raise immediately. But here's where image processing becomes critical. Astronomers don't just point cameras at comets and post the raw frames on Twitter. They stack multiple exposures to increase signal-to-noise ratio. They stretch contrast to reveal faint features. They apply filters to separate dust from gas emissions. They subtract background stars and rotate images to account for the comet's motion across the sky. Every one of these steps, while scientifically valid, can create or enhance features that don't actually exist in physical space. Take contrast stretching. If you've got a bright coma, the fuzzy cloud of gas and dust around the nucleus, and a faint tail extending away, boosting the contrast can reveal details invisible to the naked eye. But it can also amplify noise, blend background stars into apparent structures, or create the illusion of jets where there's just uneven brightness distribution. Amateur astronomers, bless them, often push processing to extremes to bring out the most dramatic features possible, which is great for aesthetics, less great for rigorous analysis. Recent high-resolution images of 3i Atlas from professional observatories, not the heavily processed amateur shots flooding social media, show a complex coma structure with multiple jet-like features extending from the nucleus. These jets rotate with the comet's spin, appearing and disappearing as active regions on the surface turn toward or away from the sun. Some jets do appear to extend in directions that initially seem sunward, but detailed geometric analysis reveals they're more accurately described as perpendicular to the expected anti-solar direction, caused by the comet's rotation and the specific viewing angle from Earth. There's also the question of what's actually causing these features. A tail can be dust particles, which behave differently based on size, or ionized gas, which follows magnetic field lines in the solar wind. Small dust grains get pushed away from the sun rapidly. Larger chunks, boulders essentially, barely move at all and can create fan-shaped structures. Gas molecules get ionized by ultraviolet light and swept away by the solar wind into long, straight iron tails. Mix all these components together, view them from Earth at a specific angle, and you can get structures that look nothing like the simplified diagrams in textbooks. Now turn your telescopes to SWAN. This comet, brightening rapidly after discovery, quickly became a target for both professional and amateur imaging. Reports flooded in describing extended tails, coma structures, possible fragmentation or outbursts. And yes, some images appeared to show morphological similarities to 3i Atlas. Similar fuzzy coma, similar tail extensions, similar confusion about what was pointing where. But here's the critical question nobody wants to answer definitively yet. Are we looking at genuinely similar physical structures, or are we looking at different structures that happen to produce similar looking images from Earth's specific vantage point? Because those are radically different scenarios with radically different implications. Projection effects are a nightmare in astronomy. You're collapsing three-dimensional structures into two-dimensional images. A tail extending perpendicular to your line of sight can look completely different from one extending toward or away from you. A jet angled 45 degrees might appear sunward when it's actually not. And when you've got two comets at different positions in their orbits, different distances from Earth and the Sun, different orientations of their rotation axes, the odds that genuinely different physical structures could produce superficially similar images are actually pretty high. Professional astronomers analysing 3i Atlas have used techniques like rotational subtraction, where you take images separated by the comet's rotation period and subtract them to reveal non-rotating features. They've applied point spread function corrections to account for how starlight and comet light blur through Earth's atmosphere and telescope optics. They've separated dust and gas components using narrowband filters tuned to specific emission lines. The result is a much more nuanced picture than sunward tail. What they're seeing is a comet with active jets on its surface, probably driven by sublimation of supervolatile ices like carbon monoxide or carbon dioxide, which vaporize at much lower temperatures than water ice. These jets create curved structures in space as rotating areas turn on and off. Dust particles ejected by these jets follow ballistic trajectories influenced by the comet's weak gravity and solar radiation pressure. The overall effect, viewed from Earth at a specific geometry, can create apparent tail-like features pointing in unexpected directions. Has anyone done this same detailed analysis for SWAN yet? Not publicly. The comet was only discovered in September, and high-resolution, multi-filter, professional observatory time is a limited resource. Most current images of SWAN are from amateur astronomers or survey telescopes, which means heavy processing, lower resolution, and more ambiguity about what's real versus what's artifact. So when people claim SWAN is mimicking 3i Atlas, what they're often comparing are processed images of varying quality, taken with different instruments, under different conditions, showing comets at different stages of their activity cycles. That doesn't mean the resemblance is fake, but it does mean we need to be much more careful about declaring it meaningful, because telescopes don't lie, but image processing can definitely mislead. The next piece of the puzzle requires moving beyond pretty pictures to something much harder to fake or misinterpret: the chemical fingerprints hiding in starlight. Part 4. Composition and spectral clues: what 3i Atlas and SWAN are made of. Chemistry doesn't lie. You can fake a photograph, misinterpret an image, or cherry-pick data to support a narrative. But you can't fake spectroscopy. When light passes through or bounces off gas and dust, atoms and molecules leave their fingerprints in the form of absorption or emission lines at specific wavelengths. It's as unique and reliable as DNA evidence in a criminal trial, which is why the compositional data for 3i Atlas is causing so much excitement and confusion in the scientific community right now. James Webb's Space Telescope turned its infrared eye toward 3i Atlas in 2025, and what it found was genuinely strange. The comet's coma, that cloud of gas surrounding the nucleus, is dominated by carbon dioxide. Not water, carbon dioxide. For context, most solar system comets are water-rich. Their nuclei are sometimes called dirty snowballs because water ice makes up a huge fraction of their mass. When they approach the sun and heat up, water vapour dominates the coma composition. You see strong emission lines from hydroxyl radicals, the OH fragments that form when sunlight breaks apart water molecules. 3i Atlas doesn't follow that script. Its carbon dioxide to water mixing ratio is unusually high, significantly different from typical solar system comets. Webb's spectroscopy also detected carbon monoxide, water vapour obviously still present but not dominant, and a cocktail of organic molecules. Complex carbon-bearing compounds that suggest this comet's ices formed in a very different environment from our local neighbourhood. There's a leading theory for why 3i Atlas looks this way chemically. Interstellar space is not empty. It's filled with cosmic rays, high-energy particles, mostly protons, accelerated to nearly the speed of light by supernovae and other violent events. When these particles slam into icy bodies drifting between stars, they deliver enormous energy to surface layers. This radiation processing can break apart water ice molecules, drive away hydrogen, and leave behind an outer crust enriched in carbon dioxide and organic residues. Think of it like sunburn, but from the galaxy instead of the sun. Over millions of years of interstellar travel, the outer layers of 3i Atlas got cooked by cosmic rays, transforming its surface chemistry into something unfamiliar. When it entered the solar system and began heating up, those processed layers started sublimating first, releasing carbon dioxide-dominated gas. Deeper inside, there's probably still plenty of water ice, but what we're seeing now is that irradiated outer shell. Polarimetric observations add another layer of weirdness. When you measure how light reflected from the comet is polarized, you can infer properties of the dust particles in the coma, things like size, shape, and composition. 3i Atlas shows what astronomers describe as a deep negative polarization branch at small phase angles, the angle between the sun, the comet, and the observer. This polarization signature is unprecedented among well-studied comets. It suggests dust particles with unusual shapes or compositions, possibly organic-rich aggregates, or ice grains with strange surface properties. There's also ultraviolet observations that detected hydroxyl, the OH emission that signals water vapor presence, at distances greater than 3 astronomical units from the sun. That's weird because water ice doesn't usually sublimate vigorously that far out. The sun's too weak. But 3I Atlas was actively releasing water, or more accurately, icy grains that continued releasing water as they travelled outward from the nucleus, at distances where most comets go dormant. It suggests a large active area on the surface, or some mechanism for sustained volatile release that's not typical. Put all these observations together, and 3I Atlas emerges as something genuinely exotic, a comet that's been processed by the interstellar environment, carrying chemical signatures that mark it as an outsider, exhibiting behaviours that don't match our homegrown comets. It's a visitor from another stellar system's planetary disk, offering a rare glimpse into how comets form and evolve in environments different from our own. Scientifically, it's a goldmine. Existentially, it's a reminder that the universe is far more diverse than the tiny sample we've studied in our backyard. Now let's talk about SWAN. What do we know about its composition? Compared to 3I Atlas, almost nothing. Because SWAN is a newly discovered comet, still brightening and becoming accessible to high-resolution instruments, and James Webb Space Telescope time doesn't get handed out casually. You need proposals, observation schedules, peer review. As of right now, there's no publicly available spectroscopic data for SWAN showing its detailed chemical makeup. What we have are brightness measurements showing SWAN climbing through magnitude 10 to 11, making it a decent target for medium-sized telescopes and large amateur instruments. Observers report a typical comet appearance, extended coma, tail structure, maybe some fragmentation or outburst activity. But without spectroscopy, we're flying blind on composition. We don't know if SWAN is carbon dioxide rich like 3I Atlas, or water rich like most solar system comets. We don't know if its dust shows unusual polarization signatures. We don't know if it's releasing volatiles at unexpected distances. This absence of data is crucial to the whole mimicry narrative. If SWAN had been observed with the same intensity and instruments as 3I Atlas, and if its spectrum matched, showing that same weird carbon dioxide dominance, that same cosmic ray processed signature, that would be huge, enormously unexpected. Because SWAN is supposed to be a native solar system object, it shouldn't have been wandering through interstellar space getting irradiated by cosmic rays. Its chemistry should reflect formation in the solar nebula 4.6 billion years ago, followed by billions of years of slow evolution in the Oort cloud. Finding an interstellar chemical signature in SWAN would require explaining how a solar system comet acquired interstellar characteristics, which opened some genuinely unsettling doors. Contamination from interstellar dust, possible but unlikely to dominate the spectrum. Capture of an interstellar comet into a bound orbit, dynamically improbable and would require very specific circumstances. Some process acting on both comets simultaneously despite their different origins. Now we're in speculative territory that demands extraordinary evidence. But we don't have that evidence yet. For all we know, SWAN's composition is perfectly ordinary for a long-period comet. Its morphological similarity to 3I Atlas could be purely coincidental, driven by the chaotic physics of comet outgassing and dust dynamics producing similar-looking structures from completely different chemical starting points. Water-dominated coma versus carbon dioxide-dominated coma can both create extended tails and jet features under the right conditions. The frustrating reality is that we're making comparisons based on incomplete data. 3I Atlas has been scrutinized with some of the most powerful instruments in astronomy. SWAN has been photographed by enthusiasts and catalogued by surveys. That's not an apples-to-apples comparison. Until someone points Webb, or another major observatory at SWAN, and captures a detailed spectrum, we're arguing about appearances without knowing the underlying chemistry. And in science, chemistry is what matters. Because two things can look alike for completely different reasons, but their chemical fingerprints will always tell the truth. The question is whether we'll get those fingerprints before these comets fade from view, or whether this mystery will remain frustratingly unresolved. Part 5. Quick decision table. Plausible hypotheses and immediate tests. Science isn't about picking your favourite explanation and declaring victory. It's about laying out every plausible hypothesis, defining what each one predicts, and designing tests to figure out which predictions match reality. So let's do that, right now. For this comet situation, we have several competing explanations for why SWAN and 3I Atlas might appear morphologically similar. Each hypothesis makes different predictions, each can be tested, and critically, some can be ruled out with data we either have or can obtain in the next few weeks to months. Hypothesis A. Pure coincidence driven by convergent physics. This is the boring explanation, which doesn't make it wrong. The idea here is that comets, despite having different origins and compositions, can produce similar-looking features because the underlying physics of outgassing, dust dynamics, and solar radiation pressure operates the same way everywhere. Both. Comets are heated by the same sun, bathed in the same solar wind, subject to the same gravitational and radiative forces. Under the right circumstances, different volatile inventories and nucleus shapes could produce convergent morphologies. What does this hypothesis predict? First, no chemical similarity. If you get spectroscopy of SWAN, it should look like a typical long-period solar system comet, water-rich, nothing exotic. Second, the morphological similarity should be transient and dependent on geometry. As the comets move through their orbits, as Earth's viewing angle changes, the resemblance should fade. Tails and jets should evolve differently over time. Third, statistical analysis should show that this kind of coincidental similarity isn't actually that rare. When you've got thousands of comets observed over decades, some overlap in appearance is expected. How do we test this? We need independent spectroscopy of SWAN, detailed photometry tracking how its coma and tail evolve, and statistical modelling comparing these comets to the broader population. If SWAN's chemistry is ordinary and its appearance diverges from 3i Atlas over coming weeks, Hypothesis A wins. Coincidence. Case closed. Move on. Hypothesis B. Common progenitor or fragmentation scenario. This hypothesis suggests that maybe, somehow, both comets originated from the same parent body that broke apart long ago. Perhaps a larger interstellar object fragmented during a previous passage through a stellar system, sending chunks on divergent orbits. One piece, 3i Atlas, remained on a hyperbolic trajectory and is now visiting us. Another piece, SWAN, somehow got captured into a bound solar orbit, maybe through gravitational interaction with a planet or stellar encounter, and has been looping through our system ever since. What does this predict? Matching chemical composition. If they're fragments of the same parent, they should share isotopic ratios, volatile inventories, dust properties. We'd expect similar cosmic ray processing signatures if both spent time in interstellar space before one got captured. Dynamically, we'd need to find plausible scenarios where fragmentation and orbital capture are possible. Maybe there's even a meteoroid stream associated with the parent body's orbit that we can detect when Earth passes through it. Testing this requires detailed spectroscopy of both comets, orbital integration backward in time to search for possible fragmentation events, and monitoring for meteor showers associated with these comets' orbits. The major challenge is explaining the enormous difference in orbital energy. Getting from hyperbolic to bound requires shedding a lot of kinetic energy, which doesn't happen easily without invoking rare gravitational assists or dissipative processes that are hard to justify. Hypothesis C. Engineered or intentional deployment. Here's where we move into uncomfortable territory. This hypothesis suggests the comets aren't natural, objects following blind physical laws, but instead are artificial constructs or probes intentionally deployed to observe or interact with Earth and the inner solar system. The morphological similarity would be explained by shared design or function. The pincer positioning would be deliberate. It sounds like science fiction, and maybe it is, but science demands we consider possibilities we can test, even uncomfortable ones. What would this predict? Non-Keplerian motion. If these objects are under active control, their trajectories should show tiny deviations from purely gravitational orbits, accelerations that can't be explained by outgassing or other natural processes. We'd expect radio emissions, perhaps narrowband signals or non-thermal radiation inconsistent with natural comet activity. Morphological features, the jets and tails, might show repeating patterns or synchronized timing that's too regular to be random. And if they're probes, maybe they emit or reflect radiation at wavelengths suggesting artificial materials or energy sources. Testing this requires high-precision astrometry to detect tiny orbital changes, radio telescope monitoring across a wide frequency range, searches for unusual spectral signatures, and long-term observation campaigns to catch any non-random behaviour. The good news is that if this hypothesis is correct, the evidence should be unmistakable once you look for it. The bad news is that as of now, there's zero credible evidence supporting it. 3i Atlas shows outgassing consistent with natural comet activity. Its slight non-gravitational acceleration can be explained by jet thrust from sublimating ices. No radio signals, no weird spectral lines, no signs of artificial structure. But, and this is important, some scientists have speculated controversially about the possibility that 3i Atlas could deploy smaller objects as it passes through the inner solar system. This speculation is based on absolutely no evidence and has been widely criticised as irresponsible fear-mongering by most of the astronomical community. Still, it's out there, circulating in news media and online forums, which means we need to address it directly. Is there any indication that 3i Atlas or SWAN are deploying probes, satellites, or any other objects? No, none. Zero. The comets are behaving exactly as natural comets should, within observational uncertainties, outgassing, fragmenting if anything, shedding dust and gas. That's it. Hypothesis D, observational or image processing artifact. This is the skeptical hypothesis, suggesting that the morphological similarity is exaggerated or entirely constructed by how images are processed, shared, and discussed. Maybe different people using different telescopes, different filters, different processing software are seeing what they want to see. Confirmation bias amplified by social media echo chambers. Cherry-picked images that emphasize resemblance while ignoring differences. Predictions? The similarity should disappear when you compare raw, unprocessed data from multiple independent sources. Professional observatories using standardized reduction techniques should report significantly different morphologies. Over time, as more data accumulates, the consensus description of each comet should diverge, and statistical analysis should show that the claimed similarities aren't statistically significant once you account for the wide range of comet appearances and processing techniques. Testing this is straightforward. Demand raw data. Compare multiple independent observations. Use standardized image processing pipelines. Peer review. If the similarity persists under rigorous scrutiny, it's real. If it evaporates, it was an artifact. Simple. So where does that leave us? We have four main hypotheses: convergent physics, fragmentation, artificial deployment, observational artifact. Each makes testable predictions. Each can be confirmed or ruled out with specific observations. The next 30 to 60 days are critical. 3i Atlas will reach perihelion on October 30th, passing closest to the Sun and likely experiencing peak activity before it begins its outbound journey. SWAN will continue brightening and evolving as it approaches its perihelion. Telescopes around the world are watching. Spectroscopic observations are being scheduled. Data is accumulating. What we need from the global astronomy community, professional and amateur, is coordinated observation campaigns, multi-wavelength coverage, spectroscopy of both comets with comparable instruments and techniques, radio monitoring, high-precision astrometry, raw data sharing with documented processing steps, and most importantly, intellectual honesty. Report what you see, not what you want to see. Let the data decide. Because if there's something genuinely unusual happening, if SWAN and 3i Atlas are connected in some way we don't yet understand, the evidence will reveal itself through rigorous observation and analysis. And if it's coincidence or artifact, that's fine too. Science advances either way. The worst outcome would be letting speculation and sensationalism drown out the actual work of figuring out what's real. So let's watch, let's measure, let's test, and let's see what the comets have to say. Part 6. Dynamics beyond two-body, non-gravitational forces, dust/gas physics, and the illusion of synchronicity. Comets don't just fall toward the Sun and swing back out like silent passive rocks. They're active, chaotic, temperamental objects that do weird things for weird reasons. And if you want to understand why two completely unrelated comets might develop similar morphologies, you need to understand the forces acting on them beyond simple gravity. Because once you account for outgassing, radiation pressure, particle dynamics, and a dozen other messy physical processes, the universe of possible comet, behaviours explodes. Suddenly, coincidental similarity doesn't seem quite as improbable. Let's start with the basics. When a comet approaches the Sun and heats up, ices on and below the surface start sublimating, turning directly from solid to gas without passing through liquid. This gas, mostly water vapour, carbon dioxide, carbon monoxide, depending on the comet's composition, erupts from the nucleus, carrying dust particles along for the ride. The nucleus itself is tiny, typically a few kilometres across, an irregularly shaped dirty iceberg spinning in space. But the coma and tail that result from outgassing can extend for hundreds of thousands or even millions of kilometres. Here's where things get complicated. That outgassing isn't uniform. The nucleus is rotating, typically with a period of hours to days. As it spins, different regions turn toward the sun and heat up, triggering localised jets of gas and dust. These jets act like tiny rocket engines, producing thrust that can change the comet's orbit slightly. Astronomers call these non-gravitational forces, and they're a major headache for precisely predicting comet trajectories. Because unlike gravity, which is smooth and predictable, outgassing is messy, asymmetric, and depends on the comet's rotation state, surface composition, thermal properties, and a bunch of other factors we can barely constrain. Now add solar radiation pressure. Sunlight carries momentum. When photons from the sun hit dust particles in the coma, they transfer that momentum, pushing the particles away from the sun. Small particles, micron-sized grains, get pushed hard and move away quickly. Larger particles, millimetre or centimetre chunks, barely feel the push and lag behind. The result is that the dust tail spreads out, with different particle sizes following different trajectories, creating a broad fan-shaped structure rather than a narrow stream. Gas behaves differently. Molecules of water vapour or carbon dioxide don't feel radiation pressure directly because they're too small and fast-moving, but they do get ionised by ultraviolet light from the sun, and once ionised, they interact with the solar wind, that stream of charged particles constantly flowing outward from the sun. The solar wind drags ionised gas into long straight tails that point almost exactly away from the sun. These ion tails can stretch for tens of millions of kilometres, thin and bluish, when you photograph them with the right filters. So a typical comet has two tails, a broad curved dust tail made of particles following ballistic trajectories modified by radiation pressure, and a narrow straight ion tail made of ionised gas dragged by the solar wind. Except real comets are messier than textbooks. They fragment. They have outbursts where large amounts of material suddenly release. They develop jets at specific locations on the nucleus. They rotate and precess, changing which regions are active. The viewing geometry from Earth means you're projecting all this three-dimensional chaos onto a two-dimensional image, and depending on the angle, things that are physically very different can look similar. Let's apply this to 3I Atlas and SWAN. 3I Atlas has active jets detected in high-resolution imaging. These jets rotate with the nucleus, appearing and disappearing as active regions turn toward or away from the sun. The carbon dioxide-rich composition means it can release gas at large distances from the sun, where water ice would stay frozen. That extended activity creates a larger coma and potentially more complex tail structures. The dust particles ejected by these jets follow trajectories that depend on their size, the ejection velocity, and solar radiation pressure. From Earth, depending on viewing angle, some of these dust streams might appear to extend sunward, even though they are actually moving outward, but at angles perpendicular to the Sun-Comet line. SWAN, presumably water-rich based on typical comet compositions until proven otherwise, will have different outgassing behaviour. Water sublimates vigorously only when the comet is close to the Sun. Its jets and coma structure will depend on rotation rate, active area fraction, nucleus shape, all unknowns right now. But the same physics applies. Jets create dust streams. Radiation pressure sorts particles by size. Solar wind drags ionised gas. Viewing geometry projects everything onto the sky. Here's the uncomfortable question. Can these independent physical processes, acting on two different comets with different compositions and orbits, produce morphologies that look similar from Earth? Yes, absolutely. It's not even particularly unlikely if you consider the full parameter space. Imagine you've got two comets at different positions in space, both releasing dust and gas, both subject to the same sun and solar wind. There are combinations of rotation axis orientation, active region location, viewing angle, and observation timing where the projected images would show similar coma shapes and tail structures, even though the underlying three-dimensional reality is completely different. It's like photographing two different waterfalls from specific angles, where they happen to look similar in the photo, even though the terrain, water flow and rock structure are completely different. The resemblance is real in the sense that the photons reaching your camera are arranged similarly, but it doesn't imply any deeper connection between the waterfalls. They're just doing waterfall things, and you happen to catch them from angles where the result looks alike. There's also the possibility of external triggers. Suppose the Sun had a coronal mass ejection, a massive burst of plasma and magnetic field hurled into space that happened to hit both comets around the same time. That shockwave could trigger enhanced outgassing, fragmentation, or changes in coma structure simultaneously for both objects, even though they're separated by enormous distances. The timing would be coincidental based on their orbital positions, but the effect would be real. Both comets responding to the same solar event, producing similar morphological changes within days of each other. Is there evidence for this? Not specifically. Solar activity is monitored constantly, and while the Sun has been active in 2025, there's no obvious CME event that correlates with reported changes in both comets. But it's the kind of scenario that illustrates how natural processes can create apparent synchronicity without requiring any deeper connection. The chaotic, unpredictable nature of comet behaviour is both frustrating and liberating. Frustrating because it makes precise predictions nearly impossible. Liberating because it means unusual coincidences are genuinely possible without invoking exotic explanations. Two comets developing similar features at the same time. Weird? Yes. Impossible? Not even close. Once you account for all the messy physics, the rotating jets, the particle size distributions, the radiation pressure, the viewing geometry, the space of possible outcomes is enormous. And somewhere in that space, there are configurations where independent comets look similar for purely physical reasons. The question is whether SWAN and 3I Atlas occupy that space, or whether something else is going on. And that question remains frustratingly open, waiting for more data to close it one way or another. Part 7. Fragmentation theory versus independent mimicry. Could SWAN be a fragment of an interstellar parent? What if they're siblings? That's the question lurking in the back of everyone's mind who's tracking this situation. Not coincidentally similar, not responding to the same physics independently, but actually related. Pieces of the same parent body that split apart long ago and are only now, through some cosmic choreography, returning to cross paths near Earth. It's an elegant explanation that would immediately account for any morphological or compositional similarities. Fragments from the same source should look alike. The problem is making the dynamics work. Because the orbital mechanics required to turn this elegant idea into physical reality are brutally unforgiving. Let's think through what fragmentation would require. You start with a large parent body, probably a comet or small icy planetesimal, travelling through space. At some point, this parent fragments, splits apart due to tidal forces, collision, thermal stress, rotational instability, or some other disruptive event. The fragments separate, each inheriting some fraction of the parent's velocity, plus whatever additional velocity the fragmentation imparted. Those fragments then follow their own independent orbits, influenced by gravity from the Sun and planets, solar radiation pressure, outgassing forces, and potentially gravitational perturbations from passing stars if they're in interstellar space. For 3I Atlas and SWAN to be fragments of a common parent, that parent would need to have fragmented in a way that produced pieces with radically different orbital energies. 3I Atlas is hyperbolic, unbound, travelling at interstellar velocities. SWAN is bound to the Sun on an extremely elongated but closed ellipse. The difference in specific orbital energy between these two states is enormous, equivalent to many kilometers per second of velocity change. How do you get that kind of energy difference from a fragmentation event? You don't. Not from any normal breakup. When comets fragment, the pieces separate at relative velocities of meters per second, maybe tens of meters per second in violent cases. That's nowhere near enough to change orbital energy from bound to unbound or vice versa. The fragments might drift apart slowly over time, developing slightly different orbits, but they remain in the same general dynamical family. They don't jump between being interstellar and solar system natives. You could invoke an extremely energetic disruption. Maybe the parent body passed too close to a massive object, Jupiter or another star, and got torn apart by tidal forces while simultaneously receiving a gravitational slingshot that altered its orbit dramatically. Some fragments got kicked onto hyperbolic trajectories, others got captured into bound orbits. but the timing and geometry required for this scenario are incredibly specific and statistically implausible. You'd need the fragmentation to occur at just the right moment during a close encounter, with fragments scattered in just the right directions to produce the observed orbits, and then for those fragments to happen to return to the inner solar system at the same time millions or billions of years later. Let's run the numbers backward. Astronomers can integrate orbits in reverse, calculating where objects were in the past based on their current trajectories. When you do this for 3I Atlas and SWAN, their paths diverge quickly. Go back 100 years, 1,000 years, 1 million years, they're never in the same place. Their orbital planes are different. Their angular momentum vectors point in different directions. There's no moment in the traceable past where they converge to a common location where fragmentation could have occurred. You might argue that perturbations over long time scales could erase evidence of a common origin. Gravitational nudges from planets, stellar passages in the Oort cloud, galactic tides, all these effects accumulate over millions of years and can significantly alter orbits. Maybe 3I Atlas and SWAN did come from the same parent billions of years ago, and subsequent perturbations scattered the fragments into wildly different orbits. But if that's true, you'd expect to find more fragments. Dozens, hundreds of objects from the same breakup event, scattered across the solar system on related but perturbed orbits. We don't see that. We see two comets with no obvious orbital relationship and no population of siblings. There's a variant of this hypothesis that's slightly more plausible, but still problematic. Maybe SWAN isn't originally a solar system object at all. Maybe it's also interstellar, a fragment that was gravitationally captured into a bound orbit during a previous passage through the solar system. Captures happen, theoretically. An interstellar object passing through the outer solar system could, through a series of lucky gravitational interactions with planets, lose enough energy to become bound. It's rare, requiring specific geometries and multiple close encounters, but not impossible. If SWAN were a captured interstellar fragment, that would explain any compositional similarities to 3I Atlas. Both spent time in interstellar space, both got processed by cosmic rays, both carry chemical signatures of extrasolar formation environments. The morphological similarities would be natural consequences of shared origin. And the timing, both returning to the inner solar system now, could be coincidental or could reflect similar orbital periods following capture. But this hypothesis has problems too. Captured interstellar objects should be exceedingly rare. The dynamics of capture require shedding enormous amounts of energy, and most interstellar interlopers just pass through without slowing down enough to get trapped. If SWAN is a captured interstellar comet, we'd need to explain how it avoided detection during previous perihelion passages, because an object on an orbit with a period of hundreds or thousands of years should have been seen before, given how bright SWAN has become. There's also the question of other fragments. If 3I Atlas and SWAN are pieces of a disrupted parent, where's the rest of the debris? Fragmentation events produce meteoroid streams, clouds of dust and small particles that spread along the original orbit. When Earth passes through these streams, we see meteor showers. Are there meteor showers associated with either of these comets? As of now, no confirmed detections. That doesn't rule out fragmentation entirely, because the streams might be too diffuse, or positioned such that Earth doesn't intersect them, but it's a strike against the hypothesis. The alternative, independent mimicry, remains more consistent with available data. 3I Atlas is interstellar, carbon dioxide rich, cosmic ray processed, genuinely exotic. SWAN is likely a typical long-period Oort cloud comet, water-rich, unremarkable chemically, following a well-understood dynamical path. Their morphologies might look similar due to convergent physical processes, viewing geometry, or image processing effects, but that similarity doesn't imply genetic relationship. They're strangers who happen to look alike when photographed from Earth at this particular moment. Science proceeds by testing hypotheses against data. The fragmentation hypothesis makes predictions, matching composition, evidence of meteoroid streams, plausible dynamical pathways for orbital divergence, perhaps additional fragments on related orbits. As more spectroscopic data becomes available, as meteoroid monitoring continues, as orbital analysis refines, we'll be able to assess whether these predictions hold up. If SWAN's spectrum matches 3I Atlas's unusual chemistry, the fragmentation hypothesis suddenly becomes much more interesting. If SWAN looks like a normal comet chemically, fragmentation dies, Simple as that. Until then, it's a possibility worth keeping on the table, but not one that current evidence strongly supports. The universe doesn't owe us elegant explanations. Sometimes coincidences are just coincidences, and sometimes strangers really do just look alike. Part 8. The Social and Observational Pipeline. How image processing, hype, and confirmation bias build patterns. Let's talk about how we actually know what we claim to know, because in the age of digital astronomy, the line between observation and interpretation has gotten blurry. Everyone with a camera and processing software can enhance, adjust, filter, and share images that look dramatic but might not represent physical reality accurately. And when you add social media, echo chambers, and the very human tendency to see patterns where none exist, you get a perfect storm for building mysteries out of noise. Astronomical imaging isn't like taking a vacation photo. You're not pointing a phone at something bright and hitting the shutter button. You're collecting photons from incredibly faint sources over long exposures, fighting light pollution, atmospheric turbulence, and sensor noise. The raw data coming off a telescope's camera is usually dim, noisy, and underwhelming. It requires processing to reveal anything interesting. That processing is both scientifically valid and potentially misleading, depending on how it's done and what claims you make based on the result. Start with image stacking. To increase signal relative to noise, astronomers take many short exposures and combine them. This averaging process suppresses random noise while reinforcing genuine signal. Except if your target is moving, like a comet, you need to align the frames on the comet before stacking, which means stars in the background will blur into streaks. If you're not careful, those star trails can look like faint tails or jets extending from the comet. Someone unfamiliar with the technique might interpret them as real features when they're artifacts of the stacking process. Then there's contrast stretching. The human eye and computer screens have limited dynamic range. If you just display raw data linearly, bright regions saturate and faint regions disappear into darkness. So you apply nonlinear stretches, logarithmic or power law functions that compress bright areas and boost faint details. This reveals structure invisible in raw frames, but it also amplifies noise and can create illusory features, patterns in the noise floor that look meaningful but aren't. Filtering is another layer. Narrowband filters isolate specific emission lines, like the green glow from ionized oxygen or the blue from ionized carbon monoxide. These filters are powerful tools for separating gas from dust, identifying specific molecules, understanding comet chemistry. But when you process narrowband images and combine them into false color composites, you're making artistic choices about what colors to assign, how much to weight each channel, what features to emphasize. The resulting image is scientifically informative but also subjective. Different people processing the same raw data with different settings will produce images that look different and might emphasize different features. Amateur astronomers, and I say this with respect for their contributions, often push processing to extremes. They're looking for wow factor, for images that will get likes and shares on social media, for the most dramatic possible presentation of their data, which is fine for outreach and getting people excited about astronomy. It's less fine when those heavily processed images become the basis for scientific claims about comet morphology. Because at a certain point you're looking at artifacts of your processing pipeline more than reality. This is how false patterns emerge. Someone posts an aggressively processed image of SWAN, showing what looks like a jet pointing toward the sun. That image gets shared. Other observers, consciously or not, start processing their own images to bring out similar features. Confirmation bias kicks in. You're looking for the thing you've heard is there, so you adjust your processing until you see it. Someone else sees your image, processes theirs the same way, confirms the feature. Echo chamber established. Within days, the narrative is set. SWAN has a sunward jet, just like 3i Atlas must be significant. Except when professional astronomers with standardized reduction pipelines and calibration procedures look at the same raw data, they might see something completely different. Maybe that sunward jet is a processing artifact. Maybe it's real but much fainter and oriented differently than the amateur images suggested. Maybe it's variable, appearing in some images but not others depending on the comet's rotation state and outgassing activity. Without access to raw data, without documented processing steps, without understanding what filters and exposures were used, it's impossible to assess the validity of dramatic claims based on single images. This isn't a problem unique to comets. It happens across astronomy and science generally. Human pattern recognition is incredibly powerful but also prone to false positives. We see faces in random noise, we find conspiracies in coincidences, we build narratives from incomplete data, and once a narrative takes hold, especially if it's emotionally, compelling or existentially provocative, it becomes very hard to dislodge even in the face of contradictory evidence. The solution is open data and reproducibility. Share raw frames, not just processed images. Document your reduction pipeline, list the software used, the parameters chosen, the calibration steps applied. Let other people independently reduce the same data and see if they get the same results. That's how science works. Not through dramatic Instagram posts, but through boring methodical comparison of independent analyses. When multiple teams using different instruments and processing techniques all report the same feature, you can start to believe it's real. When only one person or one group sees something that nobody else can reproduce, skepticism is warranted. Professional observatories follow these practices as standard procedure. They share data through archives. They publish reduction procedures in peer-reviewed papers. They cross-check results with other instruments. Amateur contributions are valuable, genuinely so, but they need to meet the same standards if they're going to be taken seriously. Posting a heavily processed JPEG on Twitter with a provocative caption isn't evidence of anything except that you know how to use image processing software. The danger is that viral claims move faster than careful science. A dramatic image of SWAN supposedly mimicking 3i Atlas gets thousands of shares before anyone has time to check whether the features are real. News outlets pick up the story. YouTube channels make videos speculating about alien probes. Within a week, the narrative has solidified in public consciousness, even though scientists are still trying to get access to clean data to figure out what's actually happening. This is the environment we're operating in right now with SWAN and 3i Atlas. Some genuinely unusual observations mixed with probable artifacts, mixed with speculation, mixed with social media amplification. Separating signal from noise requires discipline, patience, and a willingness to say, "I don't know yet," instead of jumping to conclusions. Because sometimes the biggest mystery isn't in space, it's in the space between raw data and human interpretation, where processing choices, cognitive biases, and narrative momentum can create patterns that feel real but evaporate under scrutiny. Stay skeptical, demand raw data, question dramatic claims, and remember that the universe is under no obligation to behave the way we expect, but neither should we mistake our expectations or our image processing pipelines for reality. Part 9, the intentional hypothesis, framed, testable, but risky. Let's go there. The hypothesis nobody wants to say out loud in professional settings, but everyone thinks about when the data gets weird enough. What if these comets aren't natural? What if SWAN and 3i Atlas are engineered objects, probes, or reconnaissance platforms, or something we don't have a word for, deployed deliberately to observe or interact with Earth and the inner solar system? It sounds absurd. It probably is absurd. But science demands we consider testable hypotheses, even uncomfortable ones, and this hypothesis makes predictions we can check. Frame it carefully. This isn't about believing in alien visitors or endorsing conspiracy theories. It's about defining what we would expect to see if natural explanations were insufficient and something artificial were involved. Then we look for those signatures. If they're absent, we rule out the hypothesis and move on. If they're present, we've got a problem that demands serious attention. Simple epistemology. Don't assume. Test. What would artificial objects look like if they were masquerading as comets? First, they'd probably mimic natural comets reasonably well to avoid detection. You don't announce your presence by violating physics, obviously. You'd use outgassing or controlled venting of gas and dust to create a coma and tail, providing camouflage and making your object look like just another icy body. But there'd be limits to the mimicry. Sustained complex maneuvers would require propulsion beyond simple outgassing, which would show up as non-Keplerian acceleration, changes in trajectory that can't be explained by gravity and natural forces. High-precision astrometry can detect accelerations on the order of millimeters per second squared over time. If either comet showed systematic, non-random deviations from expected orbits beyond what outgassing models predict, that would be a flag. Not proof, because comet outgassing is chaotic and hard to model perfectly, but a flag worth investigating. As of now, 3i Atlas shows slight non-gravitational acceleration consistent with asymmetric jet thrust. Normal comet behaviour, nothing anomalous. SWAN hasn't been tracked with sufficient precision over long enough time to say definitively, but preliminary orbits are consistent with natural forces. Second, you'd expect communications or sensor activity. If these are probes, they're presumably sending data somewhere or receiving commands. That might produce narrowband radio emissions, specific frequencies that stand out against the thermal background. Radio astronomers routinely search for such signals from interstellar objects, not because they expect to find anything, but because the observation is cheap, and the payoff if you did detect something would be enormous. 3i Atlas has been observed at radio wavelengths by multiple facilities. Detections, when they occur, are consistent with natural molecular emissions, things like hydroxyl or carbon monoxide lines. No narrowband artificial signals, no modulated transmissions, nothing that screams engineered source. If it's a probe, it's either not transmitting in frequencies we're monitoring, or it's using communication methods we can't recognise, or it's staying silent. All possible, but none supported by evidence. Third, you might expect structural features visible in high-resolution imaging. Natural comet nuclei are potato-shaped icebergs, irregular and random. An artificial object might show geometric features, flat surfaces, right angles, repeating patterns. Spacecraft have characteristic signatures when you image them closely enough. Of course, no telescope currently has the resolution to see details on objects a few kilometres across at the distances we're talking about. Even the best space-based observatories see 3i Atlas and SWAN as point sources or slightly fuzzy blobs, so we can't rule out hidden structure, but we have no evidence for it either. Fourth, energy signatures. If these objects have power sources beyond what sunlight and stored volatiles provide, they might emit at wavelengths unusual for comets. X-rays, gamma rays, non-thermal infrared, anything suggesting active energy generation rather than passive reflection and emission. Observations across the spectrum so far show nothing unexpected. The light we see from both comets is consistent with reflected sunlight and thermal emission from dust, plus molecular fluorescence and emission lines from gas. Standard comet stuff. Fifth, synchronized behavior. If SWAN and 3i Atlas are part of a coordinated mission, their activities might show correlations that natural objects wouldn't exhibit. Outbursts at the same time, changes in morphology that mirror each other, timing relative to Earth's position that seems too convenient. This is harder to quantify because coincidences do happen, but systematic monitoring could reveal patterns. So far, no credible reports of synchronized activity beyond the general morphological similarity we've been discussing. Now here's where this gets socially complicated. Recently, some sources, including tabloid-style news outlets, published claims that scientists believe 3i Atlas could be deploying probes or satellites as it passes through the inner solar system, particularly targeting Jupiter's orbit. These claims are, to be blunt, irresponsible garbage. They're based on misinterpretations of speculative comments, taken wildly out of context, amplified by outlets more interested in clicks than accuracy. The overwhelming consensus among professional astronomers who've studied 3i Atlas is that it's a natural comet. Unusual chemistry? Yes. Interesting scientifically? Absolutely. Evidence of artificial origin or activity? Zero. None. The comet is outgassing, shedding dust, following physics we understand. The idea that it's deploying anything is pure fantasy, not supported by observations, contradicted by spectroscopy showing natural volatile composition, and not taken seriously by anyone doing actual research on the object. But once those claims hit the internet, they propagate. People share them. YouTube channels make videos. The narrative becomes that scientists are secretly worried about alien probes but won't admit it publicly, which is the opposite of how science works. Scientists love finding weird stuff. It's literally their job. If there were credible evidence of artificial activity, researchers would be screaming about it from every platform available, because that would be the discovery of the century. The fact that they're not should tell you something about the quality of the evidence. Still, for completeness, let's define what would actually convince scientists that artificial activity was occurring. You'd need multiple independent lines of evidence. Non-Keplerian motion confirmed by multiple observatories, radio signals at frequencies and with modulation patterns inconsistent with natural sources, spectroscopic anomalies suggesting materials or energy densities that don't occur in natural comets. repeated patterned behaviour that can't be explained by rotation and outgassing, correlation with Earth's position or other targets suggesting intentional positioning, and all of this would need to survive rigorous peer review, independent confirmation, and alternative explanations being ruled out. That's a high bar, as it should be. Extraordinary claims require extraordinary evidence, Carl Sagan's famous dictum. And right now, for both 3I Atlas and SWAN, the evidence is entirely consistent with natural cometary activity. Weird chemistry in 3I Atlas's case? Yes, but weird in ways that make sense for an interstellar comet processed by cosmic rays, not weird in ways that suggest engineering. The intentional hypothesis remains on the table as a logical possibility, but without evidential support. It's the null hypothesis we check against to make sure we're not missing something obvious. If future observations reveal anomalies that can't be explained naturally, we'll revisit it. Until then, treating it seriously means defining clear tests, not indulging in speculation or mistaking tabloid headlines for scientific discourse. The universe is strange enough without inventing mysteries. Our job is to figure out which strangeness is real and which is us projecting our fears and hopes onto ambiguous data. Because sometimes comets are just comets, doing comet things in ways we haven't seen before, and that's fascinating enough without requiring alien intervention. Part 10. Observational Program and Citizen Science Mobilization. How we watch the skies. Science isn't a spectator sport, or rather it doesn't have to be. The beauty of astronomy is that anyone with a telescope, binoculars, or even a decent camera and dark skies can contribute meaningful observations. And right now, with SWAN and 3I Atlas both active and visible, the global astronomy community, professional and amateur, has an opportunity to conduct coordinated observations that could resolve some of these lingering questions. So let's talk about what needs to be observed, how to do it properly, and why your backyard telescope might actually matter. First, priority is multi-wavelength photometry. That's a fancy way of saying measure how bright the comets are at different wavelengths over time. Brightness variations can reveal rotation periods, outburst events, changes in activity level. Use standard filters, Johnson BVRI or SDSS UGRIS, to get calibrated measurements. Log your observation times, exposure lengths, telescope aperture, seeing conditions, everything that affects the data quality. Submit your measurements to centralized databases like the Comet Observation Database or the AVSO International Comet Quarterly, so professional researchers can compile light curves from multiple observers. Why does this matter? Because if SWAN and 3I Atlas show correlated brightness changes, outbursts happening at the same time for both comets despite their separation, that would be significant. It might point to a common external trigger, like a solar event affecting both, or it might be coincidence, but you can't know without the data. One observer seeing an outburst isn't enough. You need multiple independent confirmations, time-stamped, to establish that something real happened. Second priority is spectroscopy. This is harder for amateurs because it requires specialized equipment, but it's not impossible. Gratings and prisms can disperse comet light into spectra, showing emission lines from different molecules. If you can get spectra of SWAN showing which gases are present and in what ratios, that directly addresses the compositional question. Does SWAN look like a typical water-rich comet, or does it show carbon dioxide dominance like 3I Atlas? That single piece of data could confirm or rule out half the hypotheses we've discussed. Professional observatories with large apertures and sensitive spectrographs should be prioritizing this. James Webb, Keck, VLT, Gemini, any facility with near-infrared or optical spectroscopic capability needs to point at SWAN and collect data comparable to what's been obtained for 3I Atlas. Publish it quickly, make the data publicly available, let the community analyze it from multiple angles. Time is limited. These comets are brightest and most active now. Miss the window and the opportunity is gone. Third priority is high-resolution imaging. Not heavily processed social media photos, but carefully calibrated images with documented reduction procedures. Use rotational subtraction techniques if the comets are rotating fast enough. Take sequences over hours to catch jet activity as the nucleus spins. Separate dust and gas using narrowband filters. Log your processing steps so others can reproduce your results, or challenge them if they disagree. Particularly valuable would be coordinated imaging campaigns where multiple observers around the world image the same comet at the same time. This eliminates ambiguities about whether features are real or transient. If 5 observers on 3 continents all see a specific jet feature in images taken within an hour of each other, that feature is real. If only one person sees it, skepticism is warranted. Fourth priority is radio observation. This is largely the domain of professionals because it requires large dish antennas and sensitive receivers, but radio astronomy clubs and university departments can contribute. Monitor for molecular emission lines. Hydroxyl at 1667 MHz. Carbon monoxide at 115 GHz if you have millimeter wave capability. Search for unexpected signals, narrowband emissions, anything anomalous. Null results are still results. Knowing what's not there is as important as finding what is. Fifth priority is astrometry. Precise position measurements over time to refine orbits and detect non-gravitational forces. This requires care because atmospheric refraction, tracking errors, and calibration issues can introduce systematic errors. Use stars with known positions to calibrate your astrometry. Submit positions to the Minor Planet Center with realistic error bars. Don't claim precision you don't have. Honest uncertainty estimates are more valuable than overconfident wrong data. Sixth priority is meteoroid monitoring. If SWAN or 3i Atlas shed significant amounts of material, and if Earth's orbit intersects those debris streams, we might see meteors. Meteor cameras, radio reflection meteor detection, visual counting by experienced observers during predicted peak times, all useful. Meteors associated with these comets would have specific radiants, apparent origin points in the sky, and entry velocities determined by the parent body's orbit. Detecting such meteors would confirm material is being shed and give clues about fragmentation history. Let's sketch a timeline for the next 60 days, because that's the critical observation window. 3i Atlas reaches perihelion October 30th. Expect peak activity around that time, maximum outgassing, brightest coma, most dramatic tail development. The weeks bracketing perihelion are prime time for intensive observation. SWAN's orbit puts its closest approach somewhat later, but it's already brightening and active now. Coordinate observations to cover both comets regularly, not just during dramatic moments, but steady monitoring to catch baseline behavior and compare it to outburst periods. Create alert networks. If someone observes a sudden brightness increase, fragmentation event, unexpected morphological change, or anything unusual, share that information quickly through channels like the Astronomers Telegram, Comets mailing list, or social media with appropriate hashtags. Other observers can then follow up immediately while the event is ongoing. Fast response is critical for catching transient phenomena. Emphasize data quality and transparency. Post-processed pretty pictures are fine for public outreach, but if you're making scientific claims, provide raw data, or at least detailed methodology. Be honest about limitations. If you're not sure whether a feature is real or artifact, say so. Science advances through collective effort and mutual criticism. Fragile egos that can't handle being corrected have no place in this process. Finally, remember why this matters. Whether SWAN and 3i Atlas turn out to be genuinely connected, coincidentally similar, or completely unrelated, the observations we collect now will inform comet science for years to come. We're watching interstellar and solar system comets simultaneously, active at the same time, providing a rare opportunity for comparative studies. That's valuable regardless of whether there's a deeper mystery to solve. Every data point is a piece of the cosmic puzzle. Every careful observation brings us closer to understanding how these ancient icebergs behave and what they can tell us about the broader universe. So if you have the tools and the clear skies, get out there, watch, measure, document, share. Because the next chapter of this story is being written right now, and you can help write it. Part 11. What 3i Atlas teaches us. Cosmic rays, ancient ices, and the diversity of interstellar visitors. Let's step back from the mimicry mystery for a moment and appreciate what 3i Atlas represents, regardless of its relationship or non-relationship to SWAN. This object is only the third confirmed interstellar visitor we've detected, after Oumuamua in 2017 and Borisov in 2019. Each of these visitors has been strange in its own way, challenging expectations and expanding our understanding of what exists in the galaxy, beyond our solar system's boundaries. And 3i Atlas might be the weirdest yet. Oumuamua was the first, the one that broke the seal on the idea that interstellar objects are detectable, and not just theoretical curiosities. Its bizarre elongated shape, tumbling rotation, slight non-gravitational acceleration, lack of detectable outgassing despite that acceleration, all combined to make it one of the most controversial astronomical discoveries in recent memory. Proposals range from exotic ice compositions to nitrogen icebergs to, infamously, artificial light sails. The data was sparse, and Oumuamua was gone before anyone could get detailed observations, leaving us with more questions than answers. Borisov was the second, arriving in 2019, and it looked much more like what we expected an interstellar comet to be. Active coma, obvious outgassing, composition similar to solar system comets based on spectroscopy. It behaved normally, followed predictable physics, and generally reassured astronomers that interstellar comets weren't all going to be as weird as Oumuamua. Borisov was a comet we could understand, just one that happened to come from another stellar system. 3I Atlas is the third, and it's splitting the difference between those extremes. It looks like a comet, acts mostly like a comet, but chemically it's different enough to be genuinely puzzling. That carbon dioxide dominance, the cosmic ray processed outer layers, the unusual polarimetric signature, the extended water activity, these aren't features you see in typical solar system comets. They mark 3I Atlas as something shaped by a different environment and a different history. The cosmic ray processing is particularly revealing. When you're drifting through interstellar space for millions of years, you're exposed to galactic cosmic rays with no stellar wind or magnetic field to shield you. Those high-energy particles slam into your surface, breaking chemical bonds, driving away volatile elements like hydrogen, leaving behind a crust enriched in more stable molecules like carbon dioxide and complex organics. It's radiation damage on a cosmic scale, writing the history of the object's journey into its surface chemistry. This tells us that 3I Atlas has been wandering for a very long time, not a recent ejection from a nearby stellar system, but an ancient traveller, possibly millions of years in interstellar transit. That raises questions about where it came from originally. Was it ejected from a planetary system during formation, scattered outward by gravitational interactions with giant planets? Was it part of a stellar encounter where two star systems passed close enough to exchange material? Or has it been drifting for so long that its birth system is unidentifiable, lost in the galactic crowd? We may never know. The number of stars in the Milky Way is so vast, roughly 200 billion, and the space between them so immense, that tracing an individual interstellar object back to its origin is nearly impossible without extraordinary luck. We can constrain the general direction it came from, we can estimate travel times based on velocity, but pinpointing a source star requires precision we don't have. What we can learn is what this diversity of interstellar visitors tells us about planetary system formation and evolution across the galaxy. Every stellar system probably produces comets and icy planetesimals during its formation phase. Gravitational interactions scatter some of those objects outward, ejecting them into interstellar space. Over billions of years, the galaxy fills with these orphaned icebergs, a population of rogue comets drifting between stars. We're only now beginning to detect them as they occasionally pass through our solar system. The diversity we're seeing, Oumuamua's strangeness, Borisov's normalcy, 3I Atlas's exotic chemistry, suggests that comet formation processes vary widely, depending on local conditions in different planetary systems. Disk temperature, composition of the primordial nebula, radiation environment, timing of planet formation, all these factors influence what kinds of icy bodies form and what chemistry they carry. 3I Atlas may represent a class of comets that form in colder or more radiation-intense environments than our solar system, enriched in carbon dioxide and organics from the start, then further modified by cosmic ray processing during interstellar travel. This has implications for astrobiology and the chemistry of life. Comets are thought to have delivered water and organic molecules to early Earth, seeding our planet with the raw materials for life. If interstellar comets like 3I Atlas carry different organic inventories, shaped by different formation environments, they might deliver different prebiotic chemistry. Panspermia, the idea that life or its precursors can spread between worlds via comets and meteorites, becomes more interesting if the chemistry varies so widely. Maybe some stellar systems receive organic-rich deliveries that kickstart biology more readily than others. There's also the practical question of how many interstellar objects are passing through undetected. Survey telescopes have gotten much better, but they're still limited in sensitivity and sky coverage. For every interstellar comet we detect, dozens or hundreds might be passing through too faint or too distant to catch. Estimates suggest that at any given time, there might be several interstellar objects closer to the Sun than Neptune, just below our detection thresholds. Future survey systems like the Vera-Rubin Observatory, which will begin operations soon, will dramatically increase detection rates. Its large mirror and wide field of view will catch fainter, more distant objects, potentially discovering dozens of interstellar visitors per year instead of one every few years. That flood of data will let us characterize the population statistically, answering questions about size distributions, composition ranges, orbital properties, and how many interstellar comets versus asteroids are out there. 3i Atlas is a preview of that future, a reminder that the solar system isn't an isolated island, but a crossroads where material from across the galaxy occasionally passes through. Each visitor is a sample of conditions elsewhere, a messenger carrying chemical and physical information encoded in its structure. And even if it turns out to have no connection whatsoever to SWAN, even if the morphological mimicry is pure coincidence or artifact, 3i Atlas remains one of the most scientifically valuable objects we've had the chance to study. Because it's not from here, and anything not from here, by definition, teaches us something about the broader cosmos we can't learn by staring at our own backyard forever. The universe is diverse, stranger and more varied than our limited experience suggests. Every interstellar visitor is a window into that diversity, and we should be grateful for the view, even when it raises more questions than it answers. Part 12. When planets and comets collide. Recent surprises in planetary atmospheres and solar system dynamics. This year, the James Webb Space Telescope offered an extraordinary reminder. Even the planets in our own solar system, worlds we've studied for decades, can surprise us in ways we never anticipated. In March of 2025, Webb revealed something that scientists had been predicting for years, yet had never observed directly: auroral activity flickering across Neptune's atmosphere. This wasn't a vague hint or an indirect measurement. Webb captured distinct emission lines from the trihydrogen cation, H3+, a chemical signature long anticipated, but until now, elusive. It was a first-of-its-kind observation, a revelation that reshapes how we think about the outer solar system. These auroras are unlike anything we see on Earth, or even Jupiter. On our planet, auroras are confined to the polar regions, driven by interactions between the solar wind and the magnetic field, funneling charged particles toward the poles. Jupiter's auroras are massive, swirling beacons, still largely polar, amplified by the planet's enormous magnetic field and its volcanic moon, Io feeding charged particles into the system. Neptune, by contrast, defies these analogies entirely. Its auroral displays dance across mid-latitude regions rather than hugging the poles. This unexpected pattern is a direct consequence of Neptune's wildly tilted magnetic field, which leans roughly 47 degrees away from its rotational axis, a tilt so extreme that it fundamentally reshapes how charged particles flow through the magnetosphere. Webb didn't stop at capturing auroral imagery. The telescope provided a high-resolution spectrum, revealing details that were impossible to glean from previous flybys or Earth-based observatories. One of the most startling findings: Neptune's upper atmosphere has cooled dramatically since the last detailed measurements were made by Voyager 2 in 1989. The H3+ emission lines indicated that the ionosphere is now nearly half as warm as it was when Voyager passed through. This cooling is not a trivial detail. It fundamentally alters how the planet radiates energy, how particles move through its upper atmosphere, and why auroras were invisible for decades despite being predicted. The discovery reminds us that even giant, seemingly stable planets are dynamic systems, evolving on human observable timescales. Why does this matter to our story of interstellar and solar system comets? Because it illustrates a larger truth. The solar system is not a static, unchanging stage. Planets, moons, comets, and icy bodies are all active, responsive, and dynamic. If a heavy ice giant like Neptune, a planet with mass 17 times that of Earth, can undergo significant atmospheric changes in just a few decades, it's reasonable to suspect that smaller, more delicate objects, such as comets, are even more susceptible to transient influences. Consider the environment through which 3i Atlas travelled as it passed through our inner solar system. the sun wasn't idle. Charged particles, solar wind, cosmic rays, and occasional solar storms bombarded the system. These forces interact not only with planets, but also with comets' tenuous atmospheres and dust tails. The delicate balance of sublimating ices, dust grains, and outgassing jets can shift dramatically depending on local solar activity. Just as Neptune's auroras became detectable only when upper atmosphere temperatures changed, cometary features like tail orientation, jet formation, and coma brightness may be more variable than we realise, highly sensitive to external conditions that shift on days, months, or even years. This discovery of Neptune's auroras also shrinks the conceptual distance between planets and comets. We often think of planets as massive, slow-changing objects, and comets as ephemeral wanderers, small and easily perturbed. But both respond dynamically to external forces. Magnetic fields, radiation, solar wind, and cosmic ray exposure act on every object in the solar system, albeit in different ways. Planets may experience atmospheric cooling or auroral shifts, while comets may flare, fragment, or produce unusual outgassing patterns. The underlying principle is the same. The solar system is alive with forces that continually shape, alter, and sometimes surprise. This leads to a provocative possibility. Comets like 3I Atlas and even SWAN may carry tiny frozen snapshots of the solar system's fluctuating environment. Their compositions and behaviours could reflect not only their own primordial formation, but also the changing conditions they encounter. A comet is not merely a relic of its birthplace. It is also a sensitive recorder of the journey it undertakes, a particle-sized diary of radiation exposure, solar wind interactions, and magnetic influences. Perhaps what we observe in the brightness of a tail, the sudden flare of a jet, or a subtle asymmetry in the coma, is a reflection not only of internal chemistry, but also of transient external forces acting in real time. If this is true, then every observation of a comet becomes a data point not just about that specific object, but about the broader environment it traverses. The ephemeral nature of auroras on Neptune mirrors the ephemeral shifts we might see in comets. Observations that capture the system at one moment may be radically different a week later, underscoring the importance of continuous monitoring and multi-wavelength campaigns. Optical imaging, spectroscopy, and ultraviolet measurements become tools not only for cataloguing comets, but for understanding the living, breathing system they pass through. The implications extend further. Understanding that the solar system is in constant flux reframes the way we interpret anomalies in comet behaviour. A sudden brightening of 3I Atlas may not be evidence of anything exotic or engineered. It could simply be the comet's natural response to a transient solar event, an ephemeral flicker of energy cascading through the coma. Even the mimicry of SWAN and 3I Atlas could be shaped by shared environmental factors rather than by inherent similarities in their origins. In this context, similarity does not imply identical birthplaces. It may instead indicate the universe's influence at work, sculpting observable features in ways we are only beginning to understand. Ultimately, the lesson is humbling. Our solar system is not a static backdrop against which comets, planets, and asteroids pass. It pulses, shifts, and evolves. Neptune's auroras, previously invisible, now suddenly illuminated by Webb's gaze, remind us that what we don't know far exceeds what we think we know. This uncertainty ripples outward, influencing our interpretation of comets, interstellar visitors, and every object drifting through the void. It is a cautionary tale about the limits of assumption, and a call to maintain curiosity, rigour, and patience. As we continue to observe 3I Atlas and SWAN, it is essential to remember that the cosmos surrounding them, and surrounding us, is alive. Forces unseen, previously undetectable, can produce effects that challenge predictions and expectations. In this living environment, surprises may lurk where we least anticipate them. A subtle flare in a comet tail, a sudden shift in auroral brightness, or a fleeting change in an exoplanet's atmospheric signature may all be signals of a solar system that is not merely a collection of static bodies, but a dynamic, ever-evolving ecosystem of matter, energy, and light. The discovery of Neptune's auroras invites us to expand our perspective, to see comets and planets as participants in a shared dance with the Sun and the galaxy, each responding to forces that span immense distances and timescales. It reminds us that science is not about certainty. It is about observation, inference, and humility in the face of a cosmos that refuses to be fully tamed. And it leaves us with a tantalizing thought. If a distant ice giant can surprise us after decades of study, what other revelations await in the quiet, icy reaches where comets drift silently, carrying their frozen stories through the ever-changing solar system? Part 13, Radio, Astronomy and Comets. How new techniques are transforming what we can detect. Our window into distant worlds has been radically widened, not simply by looking inward at our solar system, but by looking outward, far beyond the orbit of Neptune and even beyond the confines of our own star. In 2025, astronomers using the James Webb Space Telescope alongside other cutting-edge instruments have reached a level of detail in exoplanetary characterization that was previously unimaginable. For the first time, we can probe the atmospheres of distant planets in a way that allows us not just to detect their presence, but to map their chemistry, temperature structures, and even hints of weather patterns. Each new discovery is a revelation, a reminder that the diversity of planetary systems exceeds anything we might have imagined a mere generation ago. One of the standout cases is WASP 166b, a planet classified as a hot super Neptune. This world orbits so close to its parent star that a single revolution takes only about 5.5 Earth days. The radiation it receives is staggering, orders of magnitude stronger than anything experienced in our solar system. Observations have revealed a volatile, dynamic atmosphere, brimming with water and carbon dioxide, molecules we often associate with habitability or Earth-like conditions, yet existing in an environment that is far from hospitable. The mere presence of H2O and CO2 in such a furnace challenges our traditional models of atmospheric retention and chemical stability. It forces us to rethink the limits of planetary atmospheres under extreme radiation, heat, and tidal forces. WASP 166b is not just another exoplanet. It is a laboratory for testing theories of atmospheric chemistry under conditions we could never replicate on Earth. Then there is TOI 270d, a smaller, more modest planet in terms of size, but perhaps even more intriguing from a scientific perspective. While it doesn't boast the blistering heat of WASP 166b, models suggest that TOI 270d harbours a deep, scorching atmosphere enveloping a rocky interior. Some simulations even raise the possibility of a magma ocean beneath a dense veiled atmosphere, a scenario that challenges our conventional distinctions between rocky and gaseous worlds. This planet demonstrates that size alone does not dictate the nature of an atmosphere, and that the interplay between stellar radiation, internal heat, and composition can create conditions that are both alien and extreme. TOI 270d, in its silent orbit, is a reminder that even seemingly ordinary planets can harbour extraordinary physics. Taken together, these discoveries illuminate something fundamental about the universe. Extremes are not exceptions. They are a natural consequence of the immense range of environmental conditions present across planetary systems. By observing these exoplanets, we are learning that planetary formation is a far more chaotic, varied process than classical models predicted. Volatile retention, the ability of a planet to hold onto water, carbon dioxide, methane and other gases, can behave unpredictably under the influence of heat, radiation, magnetic fields and gravity. These insights have a direct bearing on how we think about interstellar objects like 3i Atlas. If planets light-years away can sustain atmospheres we struggle to predict, then why should we assume that comets traversing interstellar space must conform to familiar chemical templates? This perspective opens the door to a profound possibility. Objects like 3i Atlas may not be anomalies at all. They could represent a broad population of weird-by-default interstellar travellers, each preserving a chemical fingerprint entirely distinct from anything in our solar system. Interstellar comets, after all, originate from the icy outskirts of other stars, shaped by radiation environments, stellar winds, and cosmic ray histories very different from our own. Their volatile inventories, the mix of ices, gases, and dust they carry, could reflect processes and histories we have yet to observe in situ. What seems strange or unique to us may, in fact, be entirely typical for a galaxy teeming with planetary systems of unimaginable variety. This also reframes our understanding of the apparent mimicry between 3i Atlas and SWAN. Perhaps it is not a fluke. perhaps it is an early glimpse of the sheer diversity of comets that exist across the galaxy. Both comets may have evolved under radically different conditions, yet still exhibit superficially similar features when observed from Earth. Their tails, jets, and dust emissions might be shaped not only by the Sun's influence, but also by inherited chemistry, interstellar irradiation, and the subtle effects of millennia spent drifting between stars. The resemblance we see could be a hint of underlying principles that govern cometary physics universally, or it could be a tantalizing coincidence. Either way, it signals that our assumptions about normal comet behavior are far too narrow. From a human perspective, this makes every new comet, every newly detected exoplanet, every uncharted object in our solar system a potential window into a larger cosmic narrative. Each object is a chapter in an anthology of planetary and interstellar diversity. They are unpredictable, uncontrollable, and infinitely fascinating. They defy our expectations and challenge us to expand our theoretical frameworks. The more we learn, the more we understand that what we take for granted, the behavior of a comet, the composition of an atmosphere, the structure of a tail, may be the exception rather than the rule. As observers, we are left to wonder what else might be drifting silently through space, far beyond our current detection capabilities, carrying chemical signatures and physical behaviors that defy our solar system-centric assumptions. Perhaps the universe is not merely stranger than we imagine, but actively inventive, experimenting with permutations of chemistry and physics on scales and under conditions that are difficult for our minds to grasp. Every new discovery, whether a hot super Neptune baking under intense radiation, a magma-wrapped rocky world, or an interstellar comet gliding silently through our neighbourhood, is a testament to this creativity. In this broader context, 3i Atlas and SWAN are not just curiosities, they are early indicators of a much larger, largely unexplored cosmic menagerie. Their study compels us to expand our perspective, to embrace uncertainty, and to recognise that our solar system, for all its familiar objects and classical laws, is just one small corner of a galaxy that is astonishingly diverse. The chemical fingerprints, atmospheric oddities, and unexpected behaviours we see may be common features of a universe where extremes are the rule, and surprises are everywhere. For the curious observer, this is both exhilarating and humbling. Every time we point a telescope, scan the skies, or examine spectral data, we are participating in a vast experiment in cosmic discovery. We are witnessing phenomena that challenge our understanding, inviting us to expand our models, reconsider assumptions, and prepare for the truly extraordinary. And in doing so, we begin to see that what we once regarded as exceptional, a comet with an unusual tail, a planet with an incomprehensible atmosphere, may simply be one instance in a galaxy full of marvels waiting to be discovered. Ultimately, the lesson is clear. The universe is far more inventive than we are comfortable imagining. It does not conform to our expectations, nor does it pause for our understanding. In the expanding window opened by telescopes like Webb, we glimpse the astonishing variety of worlds that exist beyond our solar system. And when we compare those worlds to the interstellar visitors that pass through our own neighbourhood, we realise that extremes, anomalies, and surprises are not exceptions. They are the rule. The cosmos, it seems, thrives on diversity, and every discovery is a reminder of the creativity inherent in the universe itself. Part 14. The limits of certainty, what we cannot know yet and why that matters. With all the data we've gathered, and every hypothesis we have considered, it remains crucial to acknowledge the boundaries of what we can know. The case of SWAN is far from complete. High-resolution spectroscopy is still absent from the public record, polarimetric studies have not yet been released, and detailed measurements of dust-to-gas ratios remain unavailable. Until those data are in hand, any assertion that SWAN is a chemical or physical twin of 3i Atlas must be treated as speculative. Observing a visual resemblance is not the same as confirming a shared origin or identical chemistry. In astronomy, appearances can be deceiving, and nature rarely gives away her secrets without demanding rigorous scrutiny. The tails, jets, and coma structures that capture public attention may not tell us as much as we hope. Comet morphology is a delicate interplay of multiple variables, each capable of dramatically altering the way a comet appears. The angle from which we observe the comet relative to the Sun can make a tail look sunward facing one night and antisolar the next. Dust and gas dynamics are in constant flux, responding to solar radiation pressure, particle size distributions and sublimation rates. Even minor rotations of the comet's axis can shift jets and plumes, creating entirely new patterns in a matter of hours. Two comets that appear almost identical today may diverge completely tomorrow, as ephemeral actors in a fleeting performance dictated by forces beyond human control. Solar wind, gravitational perturbations, particle collisions, and dust dispersion all conspire to rewrite their appearances constantly. We have compelling evidence that 3I Atlas's outer layers may have been processed by galactic cosmic rays. Its unusually high ratio of CO2 to water, along with spectral anomalies and polarimetric features, point to long-term exposure to radiation beyond our solar system. This evidence is robust, and it supports the idea that interstellar objects can carry a chemical fingerprint markedly different from what we see in typical solar system comets. However, even this compelling evidence does not guarantee that 3I Atlas will behave in a predictable or stable manner as it continues its solar passage. Sublimation, fragmentation, solar heating, and rotational stresses can strip, redistribute, or alter those layers in unpredictable ways. The signature we detect today may not survive perihelion, and it may be transformed beyond recognition in the coming weeks. On the far end of the spectrum, the idea that these comets could be engineered, guided, or intentionally deployed remains highly speculative. Current evidence offers no support for such a notion. No non-gravitational accelerations beyond what normal outgassing can explain have been observed. No narrowband radio signals or repeated identical jetting patterns have been detected. There are no isotopic anomalies to suggest artificial origin. Until data emerge that challenge the natural explanations, these ideas remain in the realm of imaginative what-ifs, exercises in stretching our curiosity rather than conclusions grounded in evidence. Science allows such questions to be asked, but it does not grant them credibility without supporting observations. Human perception and data processing methods add another layer of complexity to the narrative. The way images are captured, enhanced, and shared can introduce artifacts. Bright, dramatic images on social media or news outlets create expectations, which in turn produce confirmation bias. Observers begin to scrutinize every faint streak, every minor asymmetry, every digital noise pattern as if it were a clue. Sometimes, under these conditions, evidence can appear where none exists. Independent verification through raw data sharing and multiple team reductions is essential to distinguish genuine cometary features from illusions created by processing choices. Without these safeguards, the stories we build can reflect our collective imagination more than the celestial reality. Selection bias further complicates matters. Humans are naturally drawn to extremes, to objects that stand out. Dramatic tails, unusual jets, or high-brightness comets get disproportionate attention, while quieter, more mundane comets often pass unnoticed. Yet it is the quiet, unassuming comets that represent the true statistical background of the population, the majority, that defines the baseline. By focusing only on the extreme cases, our perception of what a comet normally looks like becomes skewed. We risk mistaking outliers for patterns, coincidences for causation. The cosmos does not bend to our narrative preferences. It simply exists in its full spectrum of activity. From a scientific standpoint, these factors demand humility. We must frame our conclusions as provisional, conditional upon the data available at this moment. We can say that 3I Atlas is extraordinary, and that SWAN's resemblance is intriguing. We can calculate probabilities, weigh likelihoods, and establish hypotheses. But certainty is a luxury we do not possess. The proper stance is one of provisional inference. Given the data we have, certain explanations are plausible and others are improbable, but none are definitive. This approach preserves rigour and guards against the seductive pull of sensational narratives. For the observer, the implication is clear. This story, as tantalising as it may seem, is unfinished. Each new night of observation can either reinforce suspicions or dissolve them entirely. The next weeks, months, or even years could yield transformative data. A rare spectral match might emerge, indicating a deeper connection between SWAN and 3I Atlas. Or differences might crystallise, proving that what looked like mimicry was mere coincidence. Both outcomes are scientifically valuable. because both refine our understanding of cometary behaviour and interstellar chemistry. The pursuit of understanding requires embracing uncertainty. Real discovery is not a matter of immediate certainty, but of systematically reducing the unknown. It involves asking the right questions, designing rigorous observational campaigns, analysing data methodically, and maintaining a sceptical, open-minded stance. Every comet observed, every jet tracked, every spectral line recorded is a step toward clarity. Even the anomalies, the contradictions, the unexpected outcomes, they are the clues that guide the next investigation. In the void between stars and planets, the universe does not hand out neat answers. It hands out evidence, fragmented, complex, sometimes contradictory. How we interpret that evidence will determine whether we recognise cosmic coincidence, uncover cosmic patterns, or stumble upon something entirely unforeseen. Patience, meticulous observation, and humility are the tools we wield. They remind us that knowledge is a process, not a destination. We may never fully understand the entire story of 3i Atlas, SWAN, or the countless other wanderers in the solar system, but we can learn to read the clues as they arrive, slowly and carefully, with the awareness that the cosmos often exceeds even our most imaginative hypotheses. The universe is patient. It does not reveal itself all at once, nor does it accommodate human impatience or expectation. By accepting that some doors remain closed for now, by recognising the limits of certainty and the importance of careful interpretation, we place ourselves in the position to recognise truth when it emerges. The mystery of SWAN and 3i Atlas is not a puzzle to be solved in a single night, nor even a single decade. It is a narrative unfolding on cosmic timescales, one that demands our attention, our rigour, and our willingness to watch, to record, and to wait. In this patience lies the essence of science, an unflinching confrontation with uncertainty, an acceptance that knowledge grows incrementally, and a recognition that the patterns we see may be ephemeral, coincidental, or revolutionary. By holding open the possibility of all three, we honour the universe's complexity while preparing ourselves to grasp its truths, whatever form they ultimately take. Part 15. Closing synthesis and call to action. What we know, what to watch, and how you can help. After everything we've explored, the interstellar visitor from beyond, the solar system wanderer, the strange auroras shimmering like electric bruises across Neptune's atmosphere, the bizarre chemical cocktails swirling in the skies of distant exoplanets, it's worth pausing for a moment. Not to wrap up the story, because the story is nowhere near complete, but to look around and ask, where do we stand now? What does the evidence actually tell us? And what can we realistically expect next? Let's begin with what we do know, the ground that isn't shifting under our feet, the pieces we can treat as anchor points in a universe that doesn't always play fair with expectations. We know that 3i Atlas is a true interstellar messenger, a confirmed visitor from another star system. It arrived carrying a chemical signature that doesn't map cleanly onto any typical comet class we've catalogued. The carbon-to-oxygen ratios, the dust-to-gas proportions, the hypervolatiles, all of it paints a picture of an object shaped in a nursery far from here. Its trajectory, its composition, and its behaviour have already taught us more about interstellar chemistry than every cometary mission since the early space age combined. When you study 3i Atlas, you're peering into someone else's sky, the leftovers of a planetary system we will never see. We also know that R2 SWAN, despite being a long-period comet from our own Oort cloud, remains an enigma. It may simply be another icy wanderer disturbed by gravitational tides into a sunward plunge, or it may turn out to be something stranger. For now, its uncanny mimicry of 3i Atlas, the sunward-facing tail, the plasma jet pattern, the peculiar photometric quirks, remains just that. Uncanny, interesting, but not yet proof of anything exotic. A coincidence is not impossible. Comets are chaotic, sensitive, temperamental. But coincidences this precise tend to linger at the back of the mind, refusing to go away quietly. We know that the solar system itself is still full of surprises. Neptune's newly discovered auroras are a perfect reminder. This isn't a young, dynamic world undergoing dramatic changes. It's an old ice giant, cold, distant, predictable, a planet we thought we had mostly figured out. And yet suddenly, in brand new spectral data, it lights up with energetic structures we've never recorded before. Where did the power come from? Why now? What changed? The universe likes to do this, turn the mundane into the mysterious with the flip of a magnetic field. We know that exoplanets are redefining what a planet even is. Giant hydrogen balloons with diamond rainstorms, super-Earths with suffocating atmospheres thick enough to crush steel, molten worlds that glow like iron fresh from a forge, oceans of methane, clouds of glass shards, winds that outrun sound. Our old definitions were too Earth-centred, too narrow. Every month brings new atmospheres, new chemistries, new thermodynamic freak shows that warp the boundaries of planetary physics. If nature can invent these, lightning shot through titanium vapour, convection cells the size of continents, it can certainly invent comets and interstellar objects that defy our neat categories. And with all that in mind, here's the part that matters most. This is not a spectator sport. You can participate. Yes, you. If you own a telescope, or even just a pair of binoculars and a decent camera with long exposure capability, you have more power than astronomers did a century ago. If you follow public observatory alerts, or track ephemerids, or join online communities that coordinate real-time observations, you're already halfway there. What we need next isn't a single observatory. It's a network, a swarm, a coordinated mesh of eyes and instruments across the globe. We need multi-wavelength imaging to capture optical, infrared, and ultraviolet perspectives. We need spectroscopic snapshots to catch gas release signatures and radio searches to detect odd plasma structures. We need repeated light curves, monitoring how brightness shifts over days and weeks, and careful jet tracking as outgassing responds to solar wind changes. We need measurements of dust-to-gas ratios to verify whether SWAN continues to resemble Atlas in its behaviour. We need consistency, persistence, and above all, raw data shared freely, not polished or filtered for public consumption, but the real frames, the real spectrums, the anomalies as they appear in the sky. We need to build a watch list, a timeline of key dates, including perihelion passes, opposition windows, close approaches, and periods of increased solar wind. We need to be alert whenever something looks wrong. A tail that shifts too quickly, a brightening that shouldn't happen, a plasma jet pointing at the wrong angle, a rotation state that flips unexpectedly, a morphology that mirrors another comet too closely for comfort. You can be the one who catches it. You might think that surely someone else will notice first, but that's not how science works. The unexpected almost always shows up in the margins, in the data someone nearly deleted, in the photograph someone almost threw away, in the anomaly initially dismissed as a processing error. I am not exaggerating when I say that the next big clue might come from a backyard observatory in Nairobi, from someone in a small coastal town with dark skies, from a hobbyist astronomer who has been logging observations for a decade. Astronomy has always rewarded the patient. If you participate, you are not just watching the universe, you are helping decode it. You become part of the global detective team trying to understand whether two comets, one alien, one domestic, are truly mimicking each other, or simply performing a 1 in a million cosmic coincidence dance. And if they are mimicking each other, if R2 SWAN continues to evolve in lockstep with 3i Atlas, if the jets, the spins, the tails, and the trajectories tighten in similarity, then we may be standing at the threshold of a discovery that rewrites our understanding of comet formation, interstellar chemistry, cosmic migration, or something stranger. So ask yourself honestly, if a comet from another star system and a comet from our own can imitate each other with this degree of precision, even briefly, what other patterns might be hiding in plain sight? What else is out there waiting to surprise us? The universe is bigger, older, more layered, and more unpredictable than we ever give it credit for. But this time, we are not blind. We are watching. We are equipped. We have the tools, the community, and the curiosity to confront whatever comes next. The story, this story, is nowhere near finished. In fact, this might only be the prologue. The twist that sends the narrative in a new direction might be the one you discover.